Hello, nice to meet you. My name is Myung-soo Kim, who is in charge of a technical manager for nGen. I'm planning to hold various webinars this year. Today's topics are as follows. The first topic is about using nGen links for Revit Structure. And the second topic is how to use mesh mode for analysis. And the final topic is about the modeling, design, and detailing of basement structures. Let's start with nGen link for Revit Structure. nGen link for Revit Structure enables us to transfer Revit data to Midas engine and deliver it back to the Revit for building information modeling. For compatibility with Revit Structure, Midas engine data is converted into a text file .json for the round trip. This function is provided as add-in module. Midas link for Revit Structure supports the following workflows. The first step is to send the analytical model of Revit structures to Midas engine. The second step is to import the JSON file of the Revit model in Midas engine. The third step is to export the model of engine to the JSON file. The first and last step is to import the JSON file in Revit structure as an analytical model. Using Midas link, you can import or export the model data easily. nGen link for Revit can be downloaded and installed on Midas Global Support website. The address is as follows, and please refer to the followings for the locations on the map. The following table shows which structure members can be shared between Midas engine and Revit structures and how it works in each program. The model properties such as grid, Revit informations, materials, and sections can be transferred in both directions. And most member data can also be transferred in both directions. The engine data of isolated footing and strip footing, however, cannot be imported into Revit. Also, when importing the Revit data into engine, the model is converted into the mat footing type. Revit structure provides the concept of a family format in the truss structures, but when imported into nGen, it becomes individual brace members instead of the original format. Offset information does not need to be considered here because both nGen and Revit have automatic shape offset functions. Furthermore, we are planning to develop a functions to export nGen's Revit information to Revit in the second half of this year. Here is an example I will demonstrate today. First, 3 grids exist for both directions at each level. And the model has 9 columns, 4 braces, 12 beams, 4 slabs, 2 walls, 1 foundation, and additional openings. Then let's run it. As described above, it is a model with multiple levels, grid, and various structure members. 2 levels, 3 grid, and a variety of members. After installing nGen link for Revit, I'll find and run export to nGen in the add-in. A dialog box for exporting information opens as follows. Check whether there are any abnormalities in the number of the unit, export item, and export members. In the case of materials, the value set in Revit is passed to nGen as it is. In the case of the section, it is automatically matched to the database in nGen. However, it is necessary to check whether it is imported accurately, and if you find wrong information, you should manually assign it. I'm going to explain how to assign sections directly. When the DB section is selected, one can set the DB code and section dimension. When the user section is selected, the section dimension setting is completed by matching the dimension parameters. After mapping all sections, click OK and save it as a JSON file. And load the JSON file in nGen. And you should check the number of data in the model in the import dialog box. You can check the grid and Revit information and change the member type if necessary. If there is no problem, click OK and you can figure out that the model has been imported correctly. Now let's export from nGen to Revit. The same model will be used. First, we will export nGen data as JSON file. Select the information to be exported and click OK and save it as a JSON file. Then run imports from nGen in nGen link add-in. Since it starts with a new project, first enter the project name and then load the saved JSON file. The information dialog box opens in the same way as when importing. Check information and carry out the mappings of materials and sections. Materials are assigned automatically, but in the case of sections, you must assign them yourself. To allocate a section, you need to load the family DB for the section. I will import the family DB for the L angle section from the English folder. When loading is complete, select ML angle from the family name and then select the section list. Next, I will bring H-shapes family DB. Next, we will bring another section from English folder when we load AIS section and cannot find the desired one. After selecting the newly loaded family name, find the desired section. then assigns the section of the imported family. If necessary, you can select and assign a different section. I'll import and assign the same family DB again. Next is the column. The columns are grouped into the separate folders. In the same way, I'll bring the H-shaped DB and allocate it. If you finish section mapping and click OK, you can figure out that the model has been imported correctly. If you do not have a section family, you can download it from the Revit homepage below. The address is as follows, and DB is provided for each country. And if you want to edit the text before importing the model into nGen or Revit, you can use the Json Viewer. The web version of Json Viewer can be easily found on Google. It provides an easy-to-view format so that it can be edited easily. I am going to edit the name of the material. Next, I'm going to edit the name and width of the section. Next is the mesh mode. In the previous version, one can check the mesh quality only after performing analysis. Thus, every time one wants to check the mesh quality, the analysis should be performed again, which is inconvenient and time-consuming. The newly introduced mesh mode provides the ability to check and modify the mesh size and shape. Besides, mesh creation errors in the pre-processing stage can be detected without analysis. If you run the mesh view mode, you can check the mesh shape immediately. First of all, there is a setting dialog in mesh view mode that allows you to control the overall mesh size. Here, you can set the mesh size separately for each part and determine the mesh shape. The mesh shape is categorized by the triangular and square shapes. Each model can be composed of only triangular elements or a mixture of quadrilateral and triangular elements. Next is the mesh size control function. This is a function for controlling the local mesh size. The first icon is used for the mesh size of the edge in 1D member or 2D member. And the next icon can control the mesh size of a 2D face by a member unit. Information of mesh size is saved in the tree as shown on the right and can be edited. Finally, check mesh result. This is the functions that find errors occurred in the created mesh before performing the analysis. The first option finds the cases where the mesh is created without taking into account the interference between two members. The first figure shows that the two members' meshes did not interfere with each other and the information of the two members is provided in the check result table. The figure on the right is the case with the regular mesh shape created with considering interference. The third option, find the abnormally longish element. As you know, if the element has a longish shape, we cannot get the exact result in FEM. To find the longish shape, we should enter max threshold value. The element's threshold value is the ratio of the square of the perimeter to the area multiplied by 4 pi. For example, in rectangular element, when the aspect ratio is 1:1, then the threshold value is 1.27. And when the aspect ratio is 100:1, then the threshold value is 32.47. In triangular element, when the aspect is 1:25, then the threshold value is calculated as 16.57. The check mesh result box shows the element 21 since the ratio is larger than the set maximum threshold value of 20. I will demonstrate the mesh view mode through the sample model. At this time, the mesh of the model was created to have errors in purpose. If I check the displacement shape in the analysis result, I can visually confirm a problem in the connection. To pinpoint element with problems, execute the check mesh result. When I click the list, the program flashes element as shown on the screen, so the location is easily detected. In a large percentage of this case, the problem is caused by modeling, so that modifying the model will be the solution. After modifying the model, I can confirm that the deformation shape becomes normal. When performing the mesh control again, we can check that there's no errors on the table. And let's create various mesh shapes using mesh size control. I am going to change the size of the mesh. When you click Auto Mesh, then you can see how the mesh is created. Since we used the small mesh size, the mesh becomes compact. For 2D face, I am doing the same procedure. Then we can check the mesh becomes compact again for 2D face. First, we will do the size control for the edge of 1D and 2D members. Next is the control of the 2D face. Even if a large size is entered as input, the created mesh size may be smaller than we want, since the adjacent element also affects the creation of the nodes simultaneously. Let's edit it again with a minimal value. In general, the smaller the mesh size is, the more accurate results can be obtained. Therefore, applying the smaller size only in the necessary part can reduce analysis and design time. Finally, we will set up the basement structure. Here, I will show you how to set the road, carry out the design, and create the underground structure and drawing. nGen provides a variety of members since it pursues the model-based modeling for design and drawing. Among them, we will take a look at the footing and the outer wall of the basement. Midas engine provides mat footing, isolated footing, and strip footing. Besides, we provide tools to arrange piles and pile support easily. There are two methods for footing design in nGen. Rigid design is the method that designs the footing with the same reaction force, assuming that it has infinite rigidity. FEA design is a method of performing design based on the result of FEA analysis. Two methods can be applied for mat footing and strip footing. And only FEA design can be applied for isolated footing. Soil spring and pile spring are provided to check the support of the footing. Spring property provides three types of linear elastic, tension only, and compression only. In pile spring, information on the pile diameters for punching review and the allowable support capacity for soil bearing review must be entered. And input the stiffness value for each directions for analysis. Next, I will introduce the pile placement tool. There are three methods provided. The first one is a point-based arrangement. This is a pile arrangement method for isolated footing. And we can easily place it by entering the number of piles and the spacing between piles. And the last step is select a target point. The arrangement shape according to the number of piles is as follows. And the next one is line-based arrangement method. This is the arrangement method for strip footing. If you enter the number of piles, intervals, and set the 2 point, they are automatically arranged according to the gap between 2 points. The third and last is an area-based arrangement method. This is a placement method for the mat footing. It is automatically arranged on the selected foundation member according to the spacing between the piles. Next, I will briefly explain the design of the base plate in nGen. The value, calculated from the base of the column, is used as a member forces for flexural design. The pile footing is the same. In the one-way shear design, it is assumed that the soil reaction force is transmitted directly to the column in the area inside the shear line as follows. Therefore, the one-way shear force is calculated only as of the force outside the control line and reflected in the design. The punching shear design is carried out in the same way. It reflects only the force except for the soil reaction force inside the control perimeter. Even if there is a pile, the reaction force equal to the pile area included in the control line or perimeter is ignored and reflected in the punching review. The following is a review of the stability check. Soil bearing, overturning moment, and sliding are leave for stability check. The first is the soil bearing check. The method of review is as follows. I'm not going to explain how to calculate soil bearing pressure here. The stability check for soil bearing is shown as OK or not good by comparing the allowable soil bearing pressure value set in the design parameters to the maximum bearing pressure. In the case of overturning, the sum of the moment acting on the footing and the moment caused by the shear force acting on the column is regarded as the overturning moment. The resistance moment is the weight of the footing and the soil and the axial force transmitted from the column. The overturning moment and the resistance moment divided by the safety factor are compared to check the stability. The safety factor can be entered as follows in the design parameter. Lastly, the stability condition of sliding is judged by comparing the lateral force acting on the column and the frictional force of the soil on the foundation's lower surface. The safety factor must also be considered at the same time and can be entered in the design parameter. In addition, the frictional force is calculated by multiplying the axial force of the column and the load by the self-weight of the footing by the coefficient of friction. And the coefficient of friction can be set directly as follows. Next, we will explain the input of earth pressure. Earth pressure is created as a function of level and pressure as shown in the following dialog box. Factors that affect the functions are ground level, water level, load on the ground, and internal friction angle. When a load function is created and assigned to a 2D member, the load is automatically applied according to the member's level. Earth pressure generation is calculated in the following way. It is applied according to the Jenkins theory. I will leave out a detailed explanation. To apply earth pressure according to the other theoretical equations, you can copy the values calculated according to the other tools and paste it into the table to use them. Earth pressure is applied differently in 3 places: top, side, and bottom. For the top part, the soil weight calculated through the load function and the gravitational load by live load is applied to the slab. For the side part, the lateral load from earth pressure is applied to the basement wall. For the bottom part, buoyancy to the slab is applied, which makes it possible to perform analysis and design reflecting the buoyancy. Finally, design the basement wall. For the previously input earth pressure, design results are provided for each element as follows. When designing the basement wall, it can be uneconomical to place levers identically in all areas according to the largest bending force locally. For economical design, the basic levers are added to the whole basement wall first, and additional levers are reinforced to the area where the strength is exceeded to satisfy the design criteria. Next is the lever. Reinforcing bars can be partially added to design the areas where the strength is insufficient. The design was satisfied due to the increase in the member's strength by adding the additional lever. The method of adding levers will be explained through a demonstration. Then let's look at member modeling, design, and drawing creations for underground structures. First, let's create a basement wall. Select member, thickness, and create as follows. We will create a strip footing at the bottom of the basement wall. Next is the mat footing. Let's fix the overlapping part, and let's combine the strip footing to be considered with the same design. The following is an independent foundation model. Let's select the columns to create the foundation. Next is the creation of the internal slab. Among the groups classified in the model tree, only the basement and slab will be activated. I'm going to delete the unnecessarily created slab. Then merge the slabs. The following is the input for support. Of course, you can use a source spring, but in this demonstration, I will apply pile spring. As explained earlier, you can easily enter the information through the pile arrangement tool. For the piles in column, I'm going to assign them based on the point-based arrangement. For the basement wall, I'm going to use line-based arrangement tool to assign piles. The next one is the pile arrangement for the specific area. Next, I will enter the earth pressure. First, create a function for earth pressure. Second, select a member. And lastly, enter the load for each direction. Note that when applying pressure on the basement wall, the direction must be determined according to the local axis. So the load direction must be determined by checking the local axis. Now, let's start the analysis and design process. First, create and perform an analysis case. And create a load combination. Then I will check the value of the design parameter and enter the reinforcement for each member. The reason that I cannot enter any value here is that the layer is 0. So change the layer to 1 and enter the value. Create a design case and perform the design by selecting only some of the selected part. The following error occurred because some parts do not have reinforcing bar information. Let's enter the missing information. In this case, the design process is completed successfully without errors. The red part is the member with ng. Let's check the design result. ng occurred in the shear design because the minimum reinforcement ratio is not satisfied. The result of FEM shows that large stresses are generated locally. If we design the whole model based on these large stresses, it will be over-designed as I explained earlier. So in general, we apply the average value over a certain width like this. The width is usually 2 to 4 times the thickness. We will modify the reinforcement information to satisfy the minimum reinforcement ratio. Let's redesign. Then the design of the footing is satisfied. Next is the outer wall of the basement. Looking at the design ratio for MXX of the outer wall, it exceeds 1.0 in some part. Let's add rebar for this part. So let's redesign it. You can see that the design ratio decreases, which is less than 1.0. Now let's create a drawing. In the drawing set, check the level of the list. First, I'm going to create a basic drawing. You can see that the basic shape and reinforcement information has been created. Here is the file layout. Unlike the basic drawing, the plane dimensions and level informations are displayed to determine the location of the file. Reinforcement for the slab is also created. Now let's create a section view. Create a section view by setting the desired location. Next, we will create a reinforcement map of the outer basement wall. You can check basic level and level informations as follows. Finally, let's create a floor plan for other floor. I think these drawings will be of great help in the creation of structured drawings. This is the end of my webinar. Thank you for your attention.